A single whisper from the cosmos can rewrite everything we thought we knew about the first stars, and the clues are hidden in signals we barely detect. Stay tuned, because the number one signal is something almost nobody guesses. Imagine a faint pattern of temperature variations across the sky, barely a few millionths of a degree, that holds a map of the universe's infancy. These fluctuations, first mapped by Kobe and later refined by Planck, encode density differences that later grew into galaxies and stars. By analyzing the angular power spectrum, researchers infer the amount of ordinary matter, dark matter, and the curvature of space itself. The tiniest hot and cold spots hint at quantum ripples stretched during inflation, seeding the first star-forming regions. Though the signal is subtle, its statistical imprint is robust, offering a baseline against which later signals are measured. Next up, we'll hear how a specific radio wavelength from neutral hydrogen adds another layer to this ancient story.
Surprisingly, the universe's most abundant element, hydrogen, left a faint radio fingerprint that reveals conditions before the first stars ignited. When the early gas cooled, it absorbed background radiation at a wavelength of 21 centimeters, creating a dip in the sky's brightness temperature. Experiments like EDGES have reported an unexpected depth to this absorption, suggesting that the gas was colder, or that exotic physics cooled it further than standard models predict. This signal offers a direct glimpse into the Dark Ages, a period otherwise invisible to optical telescopes. By measuring its timing and strength, scientists can constrain when the first luminous objects began heating and ionizing their surroundings. Stay tuned because the next signal bursts into view as massive stars explode in spectacular gamma-ray flashes.
Only the most massive of the first stars could end their lives in cataclysmic gamma-ray bursts that pierce the early universe's darkness. These bursts, lasting seconds to minutes, release more energy than the sun will emit over its entire lifetime, and their afterglows can be detected across billions of light-years. Models suggest that population 3 stars, forged from pristine hydrogen and helium, were tens to hundreds of times more massive than later generations, making them prime candidates for long-duration gamma-ray bursts. Detecting such events would pinpoint the birthplaces of the earliest heavy elements and map the timeline of early star formation. While none have been confirmed yet, upcoming missions aim to capture their fleeting signatures. Coming up, we'll explore tiny dwarf galaxies that act as living fossils of that primordial epoch.
Hidden among the local group, some dwarf galaxies contain stars with astonishingly low metal content, offering a window into the chemistry of the first stellar generations. These galaxies, such as Segway 1 and Boötes I, host stars whose iron abundance can be 100,000 times lower than the Sun's, implying they formed before successive generations enriched the interstellar medium. Spectroscopic surveys reveal abundance patterns that match theoretical yields from population 3 supernovae, suggesting these dwarfs preserve the nucleosynthetic fingerprints of the universe's first explosions. By studying their stellar populations, astronomers reconstruct the early star formation rate and the efficiency of metal mixing in primitive environments. Up next, we'll examine a specific emission line that lights up the early cosmos like a neon sign.
Recent observations have uncovered galaxies whose light is dominated by the Lyman alpha transition of hydrogen, a bright ultraviolet line that escapes when star-forming regions ionize surrounding gas. At redshifts beyond 6, these Lyman alpha emitters become rare because the intergalactic medium is still largely neutral, scattering the photons. Yet the handful that are detected imply that their host galaxies harbor intense starbursts capable of carving out ionized bubbles, a key step in the epoch of reionization. The line's strength and shape also encode information about gas kinematics, dust content, and the surrounding IgM's opacity. By mapping the spatial distribution of these emitters, astronomers trace the patchwork of reionization across the early universe. Next, we'll turn to the brilliant beacons of distant quasars and what their spectra reveal.
Scientists have identified quasars shining when the universe was less than 1 billion years old, their spectra acting as backlights that illuminate intervening gas. The Gunn-Peterson trough, near-complete absorption short ward of Lyman alpha, in these spectra signals the presence of neutral hydrogen, marking the tail end of reionization. Moreover, metal absorption lines within the quasar light reveal early enrichment by the first supernovae, while the width of the emission lines hints at the masses of the supermassive black holes powering them. These observations challenge models that predict slower black hole growth, suggesting that massive seeds formed very early. As we move deeper into the cosmic dawn, the next signal we'll discuss is a faint background of ripples in space-time itself.
Ancient ripples in spacetime, generated during the rapid inflationary expansion, may still permeate the cosmos as a stochastic gravitational wave background. While direct detection remains elusive, their imprint could be observed in the polarization pattern, specifically B modes, of the cosmic microwave background. If measured, these waves would provide a direct probe of physics at energies far beyond any particle accelerator, confirming inflation's energy scale and offering clues about the mechanisms that seeded the first density fluctuations. Experiments such as BICEP and the upcoming LIGHTBIRD aim to tighten the limits on this background, potentially unlocking a new window onto the universe's first fractions of a second. Beyond these ripples, the next clue lies in the uneven ionization of the early intergalactic medium.
Beyond the smooth glow of the microwave background, the universe's transition from neutral to ionized gas was anything but uniform. As the first stars and galaxies ignited, they created expanding ionized bubbles that eventually overlapped, a process known as reionization patchiness. Observations of the 21 cm line with interferometers like LOFER and the upcoming SKA aim to map these bubbles, revealing their size distribution and growth over time. The degree of patchiness informs us about the efficiency of early star formation, the escape fraction of ionizing photons, and the role of faint dwarf galaxies. By comparing simulations with the observed power spectrum of 21 cm fluctuations, researchers can reconstruct the timeline of how the cosmos cleared its fog. Coming up, we'll explore how tiny satellite galaxies preserve the chemical fingerprints of those first luminous episodes.
Finally, the faintest companions orbiting the Milky Way serve as time capsules, their stars bearing the chemical signatures of the universe's first nucleosynthesis events. Ultrafaint dwarf galaxies contain stars with extremely low metallicities, some enriched only by a single supernova, allowing astronomers to reverse-engineer the mass and explosion energy of the progenitor population 3 star. High-resolution spectroscopy of these stellar fossils reveals unusual abundance ratios, like elevated carbon or odd Z elements, that match predictions for the yields of the very first massive stars. By compiling these chemical fingerprints, scientists piece together a statistical picture of early star formation rates and the initial mass function. And now, at the pinnacle of our list, we arrive at the ultimate goal, the direct detection of the first stars themselves.
And perhaps the most thrilling signal on the horizon is the direct observation of population 3 stars, the universe's inaugural generation of luminous objects. Next-generation observatories such as the James Webb Space Telescope and the upcoming Extremely Large Telescope aim to capture the faint infrared glow of these metal-free stars, either isolated or within star clusters at redshifts beyond 10. Their spectra are expected to be unusually hot, showing strong helium and hydrogen lines with little to no metal absorption. Detecting even a single such object would confirm long-standing theoretical predictions about the masses, lifetimes, and feedback of the first stars, closing a chapter that began with the Big Bang itself. This final signal crowns our countdown, highlighting how each subtle clue builds toward unveiling the universe's earliest light.
We've journeyed from subtle temperature ripples in the microwave background all the way to the tantalizing prospect of directly spotting population 3 stars, each clue a thread weaving the story of our cosmic origins. The universe continues to whisper, and listening closely reveals how the first lights shaped everything that followed. If you enjoyed this exploration, hit like and subscribe so you don't miss the next mind-blowing list we drop each week. Which of these early universe signals changed your perspective the most? Let me know in the comments below.